In our next section, we are going to talk about IP addressing, IPv4 addresses, IPv6 addresses, and verifying and troubleshooting IP connectivity. Let's take a look at the IPv4 addresses first. IPv4 addresses are shown in dotted decimal format. As you can see that in the picture, we have 4 portions of the IP address, and portions are separated from themselves with a dot. That's why we use dotted decimal format for the IP addresses. But behind the scenes, IP addresses are 32-bit addresses. We are going to make a practical training after this video on the board about these calculations, and I'm going to show you how we calculate these numbers step by step on the board. Let's take a look to the binary to decimal conversion. We have 2 examples and we have 2 numbers in here. In example 1, I'm going to use this, and for example 2, I'm going to use this. These are binary values of the numbers. In binary values, I can use just 0 or 1. But in the decimal values, I can use the numbers from 0 to 9, as you know. Okay, let's take a look to our examples. For the first example, I'm writing this number, as you can see. And I'm writing the example 2 also, 100111101. And let's make our conversation. If I want to convert this binary value to decimal, what I'm doing is I'm writing the 2 to the 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 4, 5, 6, and 7. And I'm calculating these numbers. 2 to the power 7, 182, 6, 64, 5, 32, 16, 8, 4, 2, and 1. The last step, I'm multiplying the numbers and adding them together. For example, 1 is multiplied with 128, this, 64 with 1, 22 with 0, and I'm adding these numbers together, and here is the decimal value of the 110111010. This is 280. And if I want to convert from decimal to binary, what I'm gonna do? Here we have a reverse logic. For example, if I want to convert the 225 to decimal, I'm dividing the numbers seriously to the 2. 225 divided by 2, and as you know that quotient is 120 and remainder is 1. And I'm doing these steps, and I'm writing the binary number from bottom to up. As you can see that 111, 111, 0000, 0000, and 1. And let's take a look to the 8. I'm dividing seriously to 2. 8 divided by 2 is 4, and remainder is 0. Then 4 divided by 2, result is 2, and remainder is 0 again. 2 divided by 2, quotient is 1, and remainder is 0 again. And 1 divided to 2, quotient is 0, and remainder is 1 this time. And I'm writing from bottom to up again, and it's 0, 0, 0, 0, 1, 0, 0, 0. Alright, let's take a look to the subnet mask now. Subnetting is used to divide the network, and subnet mask is a bit mask that can be used to separate the bits of network identifier from the bits of the host identifier. We should use serial ones to represent the subnet mask, and we have some exact values that we can use when we represent the subnet mask. I'm going to show you that. But we can represent a subnet value as in a /x format or in a format like this, like an IP address. I'm going to show you that now. Here are the valid subnet mask values. As I told you in our previous slide, we should use 1111 or 1111111111, and as you can see that I can use a separate one between zeros when I'm writing a subnet mask. Okay, all bits can be 0, all bits can be 1, but that shouldn't be a valid subnet mask. Okay, I cannot separate these guys from each other. Ones are their best friends and they never lead together. Okay, if you convert this decimal values to, if you convert these binary values to decimal values, you can get these numbers easily. And if you convert this one, this is going to be 255, for example. You can give it a try. And let's take a look to the network ID. Network ID is calculated with logic and process of the IP address and subnet mask. Let's take a look what end process is. But please keep in mind that in our previous sections we have talked about that if the devices are in the same network or not. If devices are in the same network, they should have same network IDs. If network IDs are same, I never send the packet to the default gateway and I can connect over a switch. For example, this is PC1 and this is PC2 and this is PC3. Let's say that we have an IP address of 2 and this is, and let's say that this is 5. And let's say that we have all the same subnet mask, which means 255, 255, 255, and 0. If I want to calculate the network ID, I need logic AND of IP address and subnet mask. So what does it mean? I'm going to show you with a practical training test on the board. So after this session, you are going to check what I mean in here. But please keep in mind that first host address is calculated by adding 1 to the network ID, and here is how we calculate the AND process. If 2 bits that I'm using with AND are 0, or even if I have a 0 for the AND process, the AND result is always be the 0. Please keep in mind that the AND is 1 when both bits are 1. Okay, it's 0 on the any other way, but if it's 1 1, my result is only 1. And here is how I can make a dynamic IP configuration for host. I'm opening my Internet Protocol version 4 properties on my PC, and I'm choosing obtain an IP address and DNS server automatically, so I can get a dynamic IP configuration from a DHCP host server. And here is how I can make a static IP configuration for host. In this time, I'm choosing use the following IP address method, and I'm writing my values manually in this time. And here are the IPv4 host communication types. We have unicast, multicast, and broadcast, which we have talked about in our previous sections. If I want to unicast, I'm sending directly packet to B. If I want to multicast, I'm sending my packets to B or C, but not to D. if I want to send a broadcast, I'm sending my packet to all of them. So how I can make the IPv4 unicast communication? Let's see that. If computer A wants to communicate with computer C, he's choosing the source IP as his own address and destination IP as the PCC's destination IP. And the packet is only going to the computer C, not to computer B. If I want to send the multicast to the network that I'm in, reserved multicast communication IP addresses are 224.0.0.0 and 0.0.255. I need to send the packet to these IP addresses if I want to send a multicast to my network. And here is the private IP addresses and IP classes. These IP addresses, private IP addresses, are used for local area network communication and they are not globally routable. That means I cannot use this IP address range on internet because they are not globally routable. And we have class A, class B, and class C IP addresses, but classful addresses are legacy anymore. And for example, if I'm using class A, I can use these IP addresses and I just can use this subnet mask. If I'm using class C, I can use this range with this subnet mask. But this is legacy, and anymore we are using classless addressing. For example, I'm using this private IP address range, but I can use this subnet mask too without any problem. So let's take a look to the variable length subnet mask. Subnetting a network to make for the most efficient use of all of the bits means VLSN. And that's the classless addressing that I talked about. For example, you are using a range in this class C range, but you are using another subnet mask that's not in the table of the previous slide. So let's take a look to the IPv4 broadcast communication. These PCs have these IP addresses 1.10, 1.20, 1.30, and here is the default gateway for them. And network IDs for these PCs is 1.0. As I told you that I'm going to show you that on the board, how I calculate the network address detail. And the broadcast address is, for this network, is this one. I'm going to show you that again, how we calculate this on the board. And because of that, the packets destined to this IP address are sent to all hosts as communicate. For example, if PC1 needs to send a broadcast address to my network, using that source IP as 1.10 and destination as the 1.25. And let's take a look to the regional internet registries. These guys manage the allocation and the registration of IP addresses within a particular region of the network. For example, we have APNIC, we have AFRINIC in Africa, we have ARIN, we have LACNIC, and we have RIPE for a real large region. And it's time to talk about the IP version 6. As we talked about in our previous sections, IPv4 addresses are about to finish, and need will increase for IP addresses by IoT, as you know. And IPv6 provides us much more address space. As you remember that it was like undecillion, and we don't need net anymore. IP addresses, IP version 6 addresses are shown in hexadecimal format, but it's 128-bit addresses behind the scenes. In hexadecimal format, you can use 0 to 9 after A, B, C, D, E, N, F. And we can also simplify the IP version 6 notation. We have two rules about this. First one is the zero suppression rule. Strip off all leading zeros. If we have a leading zero in my IPv6 address, I can strip off this. For example, in here, as you can see, I have a leading zero. In here, I have leading zeros. So I'm stripping off them, and I can write this 0db8, and I can write just db8 instead of 0db8. This is the first rule that I can use. And the second thing is the zero compression rule, and replace the contiguous groups of zero with a column. Please keep in mind that I can make it just one time. As you can see that we have a contiguous groups of 0, and I'm writing just a column instead of this one. Sorry. And let's take a look to the IPv6 prefix length, which is used to identify how many bits of IPv6 address are there in network part. And as you can see that we have this number 64, which is represented to use to identify that the first 64 bits are in network part. IPv6 doesn't use dotted decimal subnet notation. We can just use the /x notation instead of the other one. And in IPv6, we have unicast communication again, multicast connection again, but we don't have broadcast communication in IPv6, but we have anycast communication instead of the broadcast, which means one to any, as you can see that in the picture. IPv6 unicast is the same with the IPv4 unicast. If computer A wants to send a unicast message to C, that's using source IP as its own IP address and destination IP as the computer C's IPv6 address. And we have some unicast address types of the IPv6. They are global unicast, link local, loopback, unspecified address, unique local, and embedded IPv4. Let's take a look to the IPv6 global unicast first. IPv6 global unicast address is globally unique. That's a similar logic to the IPv4 public address, and this address is routable on the internet too. And here is the address range of the IPv6 global unicast. And here's how we can configure this. Please keep in mind that if you're making IPv6 configuration, first thing you should do is using IPv6 unicast routing command and make your device ready to make IPv6 routing. Then you open the interface that you want to go in with interface command, interface fastEthernet 00. Then you type the IP address. If you would configure to IPv4, you would type IP address blah 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 and blah blah blah. This is the IP address that you'll use, and this is the subnet mask. But if you're configuring IPv6, you're typing IPv6 address instead of IP address. That's it. The rest is the same. The IP address and the subnet mask. We can make the IPv6 host global unicast configuration dynamically in two ways. The first way is stateless address auto configuration. The second method is DHCP version 6. In the stateless address auto configuration, router can send the IP address, prefix length, and default gateway information to the clients. In DHCP version 6, the DHCP server sends the IP address, prefix length, default gateway, DNS server, and the domain name information to the clients. Let's take a look at the SLAAC. The router can offer three types of informations as SLAAC type. The first one is SLAAC only. If router sends SLAAC only message, that means use the information that router sends only. If router offers SLAAC and DHCP version 6, that means use the information that router sends and get the others from the DHCP version 6 server. For example, use the information that I'm sending you, like IP address and prefix length and gateway, but get your DNS from the DHCP version 6 server. And third method is DHCP version 6 only. And in this method, router is offering that, I'm sorry man, I cannot offer you anything, just use DHCP version 6 server to get all of your informations. Let's see it with an example. For example, host is saying that, hey router, I need IP version 6 options man. Router gets the message and can offer 3 types of messages. In the first message, select only, router is saying that here is your IP prefix length and gateway. In the second method, router is offering that here is your IP prefix length, but ask DHCP version 6 server for the DNS and domain name. And here's the last step. Router can also say that, I'm sorry my friend, I don't have anything for you. Ask DHCP version 6 about all. And here we can DHCP version 6. We can take a look to the DHCP version 6 options. In this example, host is saying that, hi router, I need IP version 6 options. Router can offer that here is your IP prefix length, but ask DHCP version 6 server for DNS and domain name. Host gets the IP and prefix length from router and ask to DHCP version 6 server about DNS and the domain name. The other unicast type that we are using in IP version 6 is IP version 6 link local unicast that provides communication on the same local link. That's a similar logic to IP version 4 private addresses. And this address is assigned with prefix FE80:/64, although being defined as the block of this block. And link local unicast addresses are also being used for the next hop calculation in routing protocols. And interface ID can be randomly created or can be created with EUI64 process, which we're gonna examine in the next slide. As you can see that IPv6 link local unicast has 2 portions. First portion is this address space. This is the remaining 54 bits, and in the second portion we have interface ID, and we can calculate the interface ID randomly or with this EUI process. And let's take a look at the EUI64 process. The first step, insert FFEE to the middle of the client's MAC address. Let's say that this is my MAC address 000C 292C OC 0C 47 and D5, and the middle of the MAC address is here, as you can see. This is the middle. And I'm injecting an FFFE to the middle of the address. Then I need to reverse the 7th bit. For example, if 7th bit is 0, make it 1. If it's 1, make it 0. And establish the 64-bit device identifier. And I'm going to here 00, and I'm writing 00. This is 00. And I'm reverting the 7th bit. My 7th bit is 0, but I'm reverting it to 1. And as you can see that here is still 0, which represents here, and here represents 2. And here is my device identifier. And we have loopback, unspecified address, unique local, and embedded IPv4 address types. Embedded IPv4 helps transition to IP version 6. Unique local is used for local addressing. Unspecified address is used when the device doesn't yet have a permanent IP version 6 address. And loopback is used for sending packet to itself by a host. If I want to display the IP version 6 routing table, I'm using the show IP version 6 route. In router, IP version 6 routing tables and IPv4 routing tables are kept separately. if I want to display this, I'm using show IP route command. But if I want to display the IP version 6 routing table, I need to use the show IP version 6 route command. But we have the same logic in the routing table, as you can see that. As you will remember, that means connected, that's local, that's EIGRP, and I have also my networks and I have my next hops. That's the same logic with the IP version 4 routing table. And let's take a look to the verifying and troubleshooting the IP connectivity. The easiest method that I can verify and troubleshoot the IP connectivity is the ping command. For example, if I want to check the reachability between PC1 and PC2, I can use the ping command in PC1. I can use that ping 0.3 and check that if I have reachability to PC2 or not. I can also use the extended ping2 which has another features like that, how many times I can ping. I can specify the datagram size or timeout and blah blah blah, something like that. And here is the output of the ping command. For example, in here I'm seeing a successful ping because I'm getting reply from the remote device, and we are happy, as you see. But if you see an output like this, request timeout, that means that the remote device is not sending a reply to us, and that means here is the bad news. Time to cry, request timeout. And we have also traceroute command to verify the connectivity. Traceroute is used to test the path hop by hop. For example, if I want to test the path from PC1 to until here, I can use from PC1 to tracert 10001 command. This command will check the path hop by hop and will say me if there's a problem on the road or not. Please keep in mind that if I'm using traceroute from a PC, I need to use tracert. But if I want to use traceroute from a network device such as a switch or router, I need to use traceroute command. And traceroute has also extended options too. And here is the command output of the traceroute. For example, tracert this IP address. We can write the domain name or the IP address too. And here is the path that I'm using when I'm trying to reach to this IP address. And that means trace complete. And that shows you that we have reachability and there's no problem. But in this scenario, as you can see that I'm going to this IP address, here to, but here's the last node that I can go when I'm trying to go to this IP address. And as you can see that it's time to cry. Here is the bad news. If I need to troubleshoot that way, I don't need to check the nodes between here. I need to take a look further of here. And we have also debug command, which provides real-time troubleshooting about protocols, IOS processes, and events. But please keep in mind that you should use debug command very, very carefully, because debug command may cause high CPU usage. If you want to stop the debugs that you open, you should perform uall command, and that's your best friend. And for example, debug IPX is an example usage of the debug command. For example, debug IP rip, and you are debugging the rip message. And we have another great tool that I can use. That's the terminal monitor command, which is used to display log messages when connected via Telnet or SSH to the device. Log messages are displayed by default for just console connection, and if you want to view them in Telnet or SSH session, you need to type terminal monitor.